Welcome back to our machine design series. Today we are going to continue our discussion of bearings. We're going to take a little bit of a detour and talk about contact stresses. So in the previous video we talked about bearings and a couple different types of bearings, but no matter which type you select, a bearing is going to transfer load through contact with two separate parts. And so contact stress is what will most likely cause the eventual failure of a bearing. So to talk about contact stress in more general terms, let's just define it as any time two curved surfaces are pressed together, we say that those surfaces are in contact. Now, some common examples might include things like wheels on a rail, valve cams, tappets, mating gear teeth, and of course rolling bearings, which is what we're talking about. Failures due to high contact stress will present as cracks, pits, or flaking on the surface. And we are going to look at two special cases of contact that have closed form solutions. And they were solved through the Hertzian contact model. So the first of the two special cases that we will look at is sphere on sphere contact. Okay, so did a little bit of setup here. This is the model for our sphere-on-sphere contact. You can see that we have two spheres. The one on top has diameter d1, it has elastic modulus E1 and Poisson's ratio nu1. And on the bottom we have a larger sphere with a diameter d2 and Young's modulus E2, Poisson's ratio nu2. These two spheres are being compressed by force F on top and bottom, equal and opposite forces there, and then I've just drawn the z-axis as pointing down. The contact area between these two spheres is going to be circular. If you want to prove this to yourself, take something soft like a tennis ball and try pressing it into a desk or maybe like something made out of foam, and you will see that the impression your tennis ball leaves in that foam will be circular. The radius of contact, so the radius of that circle, is A, so I forgot to label that on our drawing here. Let's add that now. So this dimension is 2 times A, where A is equal to the cube root of 3 times F, our compressive load, over 8 times 1 minus nu1 squared over E1 plus 1 minus nu2 squared over E2. All of that divided by 1 over D1 plus 1 over D2. And I'm not going to go into detail in this section on any of the derivation. Really, I just want my students to be able to use these equations and recognize when to use the sphere-on-sphere contact model versus the cylinder-on-cylinder contact model that we'll get to in a second. The other important equation associated with the sphere-on-sphere model is the maximum contact pressure. Which is given by P max equals 3 times the force over 2 times pi times the radius of contact squared. So a couple of notes about these equations. This also works for a sphere on a flat surface. If we let the diameter representing the flat surface equal infinity, and effectively what that's going to do if we take a look at this radius of contact equation, if we plug in infinity, say for d2 here, we're going to get a 1 over infinity term in the denominator of this. 1 over infinity, that approaches 0, so we effectively will just eliminate this term. Also, these equations work for a sphere in a spherical cavity. All we have to do is let the diameter of the cavity be a negative number, and then we can use the same equation, same formula, to solve for a sphere in a spherical cavity, which maybe would be the case if we needed to model the contact between a ball and a socket joint. All right, now if we think about the stresses that are happening in these spheres, first, I think intuitively you might be able to see that the stress in the z direction, which is up and down as it's pictured here, that's going to be our maximum stress. It's compressive, but it has the maximum magnitude. And the magnitude of that stress is it's represented by this equation, negative P max over 1 plus z squared, where z squared is the distance from the contact point, so this point here in the center, to the point of interest. So how deep are you in the sphere where you're looking at those stresses, divided by a squared, which of course is that contact radius. And note that I have denoted this maximum stress with sigma 3 for the principal stress because this is the maximum negative stress, and we always order our stresses from sigma 1 to sigma 3, with sigma 1 being the most positive, sigma 3 being the most negative. And that comes from our section on Mohr circle. Okay, and then stresses in the x and y direction. If we look at our diagram here, I think you can intuitively see that those stresses are going to be equal, right? We have symmetry in the xy plane. These are two spheres after all, so they are symmetric. And we have a formula for those two stresses, which are going to also be sigma 1 and sigma 2. Now, I saw some raised eyebrows when I wrote this equation on the board in class, and I know that it is a long equation, but you know what all these variables are, right? We know that z is just the distance from the contact point, a is our contact radius, which we have an equation for up here, so we can solve for what that is. And nu is the Poisson's ratio of the material that we are looking at stresses in. So if we're trying to analyze the stresses in this larger sphere, for example, then we would use nu2 in this equation. Okay, and now the last thing that we need to do is to figure out where our maximum shear stress is going to be. And if you remember from maximum shear stress theory, we know that tau max is equal to sigma 1 minus sigma 3 over 2. And since, in our case, sigma 1 is equal to sigma 2, we also have that sigma 2 minus sigma 3 over 2 is equal to tau max, because sigma 1 and sigma 2 are the same. Now, we have a figure, which I will pull up in a second, that shows the magnitude of the stress components as a function of distance from the contact surface. So let me grab that figure. This is figure 3-38 in your textbook, and this figure plots the stresses that we've just written out equations for, right? So sigma z is maximum, right? That's just plotting this equation here as a function of z, which is the distance from the contact surface. That's what's on this x-axis. And then on the y-axis, of course, is magnitude of stress. We have that sigma x and sigma y are equal to one another, and they're plotted on this line here. And then we have our maximum shear stress, and this is where things get really interesting for contact. So tau max actually reaches a maximum about here. So it's not on the surface where these two parts intersect. Our maximum shear stress actually peaks just below the surface. So if I try to draw a zoomed in view of contact between a couple of parts, there we go. Here's our kind of contact pressure. Let me try to move this down so it actually contacts there. Now, our maximum shear stress actually occurs not, anywhere here on the surface where these two things are intersecting, but actually tau max occurs just below the surface. So approximately, there. And many experts believe that this is the cause of surface fatigue failures of contacting elements, because we have this maximum shear stress that weakens the material just beneath the surface. And then as time progresses, these cracks grow towards the surface, and eventually this chunk of material pops out of the part. And that shows up as something that people call pitting. So you'll see these little pinholes of material in the surface where we have contact fatigue. So this is a really interesting thing that comes out of Hertzian contact theory. And now let's talk about the cylinder-on-cylinder model, and then we'll talk a little bit more about surface fatigue in a second. So the other model, Hertzian contact, that we're going to use is cylinder on cylinder. So give me a minute. I'm going to set this one up. All right, so here's our model for cylinder-on-cylinder contact. We have a smaller cylinder, on the top. It has a diameter d1. It has a length of this lowercase l, and elastic modulus E1, Poisson's ratio nu1. We have a larger cylinder on the bottom here. It has a diameter d2 and Young's modulus E2, Poisson's ratio nu2. These two are being compressed by equal and opposite forces F. And I've also drawn the z-axis pointing down here. Now, when these two parts press against each other, the contact area is going to be rectangular, and it is going to have a length of L and a half width of B. So I've drawn 2B down here as the full width, half width is B, and we have an expression for B, which is given in the textbook as square root of 2 times F over pi times the length times 1 minus nu 1 squared over E1 plus 1 minus nu 2 squared over E2, all of that divided by 1 over D1 plus 1 over D2. And of course, we also want to know the maximum contact pressure. Which for a cylinder on cylinder is equal to 2 times F divided by pi times B times L. And we have similar notes to when we were looking at the sphere-on-sphere contact model. These equations will also work for a cylinder on a flat surface. And again, if we plug in d equal to infinity for one of these diameters, the one that represents the flat surface, then we're going to end up in the denominator here a 1 over infinity term, which goes to 0. This would be useful for many situations. You could think of a wheel on a rail. That would be a classic example of a cylinder on a flat surface contact model. We also may be interested in a cylinder inside a hollow cylinder. Tried to combine those words. So to model a cylinder inside of a hollow cylinder, we simply let the diameter of the hollow cylinder be negative in our equation. And this is going to be the type of model we need for a roller inside of a bearing race, for example. Now, again, we are interested in the stresses, of course, that develop inside the roller or inside both cylinders. And again, the stress in the z direction is going to be maximum. And we also need stresses in the other two directions, so sigma x and sigma y. Now, for a cylinder, sigma x and sigma y are not going to be precisely the same. So we're going to have two separate expressions for each of those. And you'll notice that I didn't designate sigma x or sigma y as sigma 1 or sigma 2, and that's because they actually sort of switch places depending on how deep you are into the cylinder. So let me pull up that same figure as we looked at for sphere on sphere, and you'll see what I mean. Okay, so here's that figure. This is figure 3-40 in your textbook. And again, we are just plotting the equations that we wrote up here as a function of z, which is the depth into the material. And so again, you'll see that sigma z is maximum always. That's the up and down direction. And then sigma y is greater than sigma x for a while. At some point, they intersect each other, and sigma y becomes less than sigma x. So if we are thinking about how to write our maximum shear stress equation, we know that our maximum shear stress is going to be sigma 1 minus sigma 3 over 2. And for a time, that is going to be sigma x minus sigma z when we're on this side of the graph. So this turns out that it is when our z is less than 0.436b, tau max is sigma x minus sigma z over 2. Then once z is greater than 0.436 times b, tau max is equal to sigma y minus sigma z over 2. So depending on how deep you are in your sample, where you're trying to, or how deep you are in your cylinder that you're trying to analyze, you may need to use this equation or this equation. Now again, we are really interested in where tau max reaches its peak, and it does that after this transition point. So you can actually see there's a little bump in the tau max graph right where this transition occurs. If I draw like a dotted line here, you can see that right where we have this transition, we get a bump in our tau max line, and but again, we're interested in where it peaks, and it turns out that this point is around 0.786b. That's the value of your x component about there. All right, so at 0.786b, we have maximum shear stress. And so again, keep in mind that this is all occurring below the surface of the actual contact point. And so again, this is believed to be the mechanism of surface failure, surface fatigue. Another thing to keep in mind is that this all assumes, even the sphere on sphere and the cylinder on cylinder, this all assumes that no shear is applied. We are just looking at the case where we have a load, a compressive load F, that's pushing the two surfaces together. Now, once you have a contact stress case with friction that provides shear, these equations will change. So some common applications of that would be the wheel-rail interface when the wheel is actually moving, and also gear teeth. You are always going to be applying some shear due to friction. For rolling element bearings, we will, in this section of the class, tend to assume that we are not applying shear with friction. So that means we're assuming that we have these really well lubricated gears, or really well lubricated rollers. But for more accurate models, you would want to include a shear component due to friction. Now, another step further into this would be to look at surface fatigue. So this is also all assuming static loading, right? Where we have not gotten to the part where we're doing fatigue due to contact. And we really won't study that in this class because it's not definitively understood. We do know from many experiments that it is related to Hertzian contact stress. So in some way, the phenomenon of surface fatigue is related to these stresses that we've derived. But it is more random, more stochastic, because if you're thinking about a rolling sphere or cylinder, those Hertzian contact stresses are going to be repeated each time you have a rotation, and so that leads to surface fatigue failure. Similar to how we discussed fatigue in Chapter 6, where we said, even if we have a tension load and we begin applying that tension load to a specimen many, many times, we will likely see failure of that specimen, or we can see failure of that specimen much sooner than if we only applied that load as in a single static form. This can also be accelerated by corrosion, adhesion, abrasion, but one thing is for sure, and that is that when you have surface fatigue, you do not have an endurance limit like we did for Chapter 6. So even for steels, even for steel rollers, we do not have an endurance limit. Your steel roller bearing will eventually experience failure. The question that we need to answer for this class and try to estimate or predict when that failure is going to occur. And also we will discuss mechanisms and maintenance practices that you can use to prevent an early failure. All right, so with that, that wraps up this video on contact stresses. In the next one, we will do an example walking through how to use these equations, and then we will get to actually speccing your bearings and how to select the appropriate bearing for your application. So I hope you enjoyed this video. I went on a bit of a tangent at the end, and I hope to see you in the next one.